Hi, and welcome to our next section here on feature selection techniques. Here I will start now introducing the filter techniques. So we'll understand how they work, how we can practically apply them to feature selection problems, and we will introduce a bunch of fairly simple methods where I think you will very quickly understand the underlying principle because you will have learned the principles elsewhere. So they are mainly based on stuff like correlation, some test statistics from things like the t-test, simple AOC calculations or mutual information, and so on. So how do filter techniques work? What do they construct? Let me actually maybe move over a little bit to the right hand side so you can also see the slide numbers. They're fairly simple. So a filter technique is simply a measure that quantifies the dependency between usually a single given feature and the target variable. So we have some function, I don't know, S, that measures here some dependence between our xj and our y. Usually we do this for individual features and we then associate a score with each individual feature that just somehow tells us how useful that feature could be in predicting y, or how much information it can be gained through its observation regarding y. And yeah, they're also, I mean, this is usually usually like it's a univariate measure, right? With that I mean just accesses xj, kind of based on usually a bivariate function, right? Because let's for example say we could use something like, I don't know, maybe xj and y are both numerical variables, so it would be in a regression setup with one numerical input and then, or with multiple numerical inputs, but we're just looking at one at the moment, and then, I don't know, maybe we measure something like, I don't know, the correlation or the absolute value or the squared correlation between xj and y. And then that number we would use as some indication of how useful xj is for predicting y. These things are model agnostic in the sense that we can combine them with any ML model, and it's kind of used as a pre-processing step. So I mean, you can use them just to kind of peek into your data set and understand a little bit about the usefulness of individual features, but usually they are used, and I guess we could plot the filter values that we have obtained in such a bar plot, and usually would sort them from large values to small ones. So we'd kind of rank the features in terms of their usefulness, and depending on how many features we have, we might be able to look at such a plot, or we just have to look at the, I don't know, the top k features, but usually this is used, I mean, the name filter is there for a reason, so we use that to kind of filter down our features to the top k most helpful and relevant ones. I'll now go through a bunch of ways of setting up these filters through various measures. I will not really go into too many details here because how a chi-square test works, how correlation works, how things like mutual information works, you can either learn here in other chapters of our lecture, or you'll have discussed that in depth in a basic course on statistics. So first thing we could do is we could test for independence between a categorical x and a categorical target y. So if our target is a classification, maybe multi-class, and we have some categorical input xj, we could now run a test of independence between xj and y. And if xj and y are independent, I guess then having the information of xj is not very useful in predicting y. How can we do that? Well, we can use the chi-squared test for that, for testing for independence in such a categorical table. So I'm not sure, well, I'm pretty sure I'm not going to read out the test statistic here. So this is just super normal. It's just the regular chi-squared thing. And we now use either the chi-squared statistics, or you can just also convert that into the value, into the p-value for the relevance of the feature. So I guess the larger the chi-squared statistic is, the more dependent the target feature is, or there are more dependencies between the feature and the target, or the lower the p-value is, the more evidence we would have collected to, I don't know, to contradict the assumption of independence. Okay. Well, maybe it's also useful to kind of discuss whether these things can also be applied for other scenarios. So what can we do if we have a numeric feature and a numeric target? Well, I guess then we can discretize them and still run the test. Of course, then the results will depend on the discretization. Well, I've already mentioned a couple of times we could also measure the correlation between a numeric input and a numeric output. So I guess that's now more geared really towards numerical variables and regression. So I guess you also know how you can compute the Pearson correlation. This is the formula. Again, remember, Pearson correlation is heavily connected with the R-squared measure. So the correlation measures how much linear dependence is between two variables. Basically tells us how good a fit of a linear model would be if we would predict one feature from the other through a linear model. And there's a different form of correlation, which is a Spearman correlation. And Spearman correlation is pretty much exactly the same thing as Pearson, but we run that not on the original feature data and the original Y data, but we run it on rank values of xj and yj. So do rank transformation for xj, rank transformation for y, and then we run Pearson correlation on that rank data. And this will also measure nonlinear dependence, but only monotonic relationships between both variables. And very often, because in these filter scenarios, we do not really care about the sign of the correlation. We usually just compute the absolute value of the correlation. And of course, now a higher value indicates higher dependence between input and output. Now, as I've already said, and hopefully you know already very well, Pearson will only measure linear dependence. Spearman is a bit more general. It will measure monotonic relationships, but arbitrary non-linear relationships cannot be captured. So this is this usual plot here, which I'm pretty sure we stole from Wikipedia. So you can see here, various different forms of bivariate data clouds. And you can also see the correlation value printed on top. And then you have instances where I guess they're pretty intuitive. So you have this thing here, like a perfect linear relationship between the two variables. And you also have a correlation value of y. And then you have stuff like this here, where apparently there is no relationship between x1 and x2 or xj and y. And we have a correlation value of 0. And then there's unfortunately stuff like that, where there's a pretty apparent relationship, but nonlinear one, between the two variables, but it still has a Pearson correlation value of 0 because, like I said, Pearson only measures linear relationships, and that's a quadratic relationship. Yeah, there's also some variants, stuff like distance correlation, which you could also use to measure nonlinear and non-monotonic dependencies, but that's a bit rarer and a bit more special. So I'm not going into the details here, but if you're interested in that, in stuff like that, you can have a look at that, at distance correlation techniques, or in a few minutes we'll also discuss mutual information as another viable alternative for measuring nonlinear dependence. Now, maybe you want to have something that's a bit more geared towards binary classification. So there's a very simple filter based on the t-test statistics. I guess it's extremely simple to explain. So here we have based on these two figures here. So, well, I guess maybe we can also start with the with the abstract stuff. So let's say we have one numeric feature and two classes in our output. So how about we say, if I now look at the distributions, the class conditional distributions of this feature, if there's maybe a big difference in mean between these two distributions, I guess then I can use the feature to characterize the two classes. And this is exactly what I'm now plotting also down here. So maybe I'm also assuming that my feature data per class conditional feature data, class conditional distribution is roughly Gaussian. Then I could run a t-test for the hypothesis of their being no difference in mean values between the two distribution versus there is actually a difference. And yeah, can now calculate the t-test statistics for that. It's fairly simple, right? And we can again either use the t-score as an indication for relevance, or we can again transform it into a p-value, and then the smaller it is, the more likely it will be that our feature is actually helpful in discriminating between the two classes. If you have imbalanced classes, we've already studied AOC as a measure for that. Usually we have used AOC as a tool for measuring the discriminating power of a scoring model or of a probabilistic classifier. So here we'll use it in a slightly different way, maybe even a simpler way. So I'm now going to take a single numerical feature, and I'm going to assume there's like two classes. So here I have my feature value, I don't know, xj, and let's say that we have actually ordered our feature, we have actually ordered our observations here maybe from large feature values to small ones. And here I would have my y column with a bunch of zeros and ones, which are my labels. And what I'm now going to do is exactly the same as I did when I used a scoring classifier and then computed its ROC curve and then its AOC values. So I'm just going to threshold this thing here, but now not based on the probabilistic output of my classifier, but just based on this raw feature value. And then for this binary classifier that I get from, maybe I shouldn't, I don't know, cut somewhere over a class, but between observations, for all of these associated and induced binary classification systems, I'll just compute their FPR and then their TPR, and I'll do that for all thresholds, and then I get curves like that here, and I get a curve for each feature, an ROC curve for each feature, and I can compute for a curve like that the AOC, so the area under such a curve, and take that now as a value of discriminating power of that feature for my binary class. So optimally it would be 1, and the higher it is, the better it would be. And if it would be at 0.5, I guess it wouldn't work much better than like having a random classifier. So I guess we could also rescale this a little bit. There are these normalized versions of AOC and so on. I guess you've understood how this works. If I have a multi-class problem, so I can't run the t-test anymore, but we can run the f-test to assess whether the expected value of a feature helps us to discriminate between now a couple of classes. And I guess I don't have to say too much more about that. It's also pretty basic. And then there's things like mutual information, which are constructed a little bit differently. So here we would kind of do something like this. So this would be the mutual information between x and y. I guess that's a little bit harder to understand, but so this is also sometimes called information gain. So if you have no idea how information theory works like and where this formula comes from and how it connects to entropy, have a look at our dedicated chapter on information theory. This is also here available on the same web page. So I'm not going to, replicate this here. What I want to say is that mutual information is actually a pretty interesting measure of dependence between two variables, or in this case an input and output variable. It measures the dependence quite nicely, because what we can actually say is that mutual information will be 0 if and only if, and that's not true for correlation, it will be 0 if and only if our features are independent. For correlation, that's actually not true. It will only be true under the assumption that our joint distribution is Gaussian, so multivariate normal. It also measures, because of this, a nicely nonlinear dependence between features. So it's not restricted to linear relationships, and also unlike correlation, mutual information can be defined both for numerical and categorical variables. For that reason, I guess, provides a more general measure of dependence, and I guess this is also why people like using that as a tool in feature filters. Can also discuss a little bit how we could estimate that. So for discrete features, we usually use observed frequencies. And then we have these discrete densities. For continuous features, binning and kernel density estimation is usually used. Estimating mutual information is not super simple and trivial for higher dimensional cases, but here we mainly use that in a bivariate setting, so for x, j, and y, and there it's actually not that problematic, both in the categorical and the discrete case and in the continuous case. So this brings us to the end of this session here. I have a second one on filters where I go a little bit more into some misconceptions about filters and some toy examples to sharpen our intuition and how we can practically apply filters in a pipeline setting and how we can also tune them together with our machine learning model.